Okay, now before the break, we stopped at a vapor species diagram. Now we talk about two-dimensional isothermal stability diagram. So I just give you some example. So this graph give you a stability diagram for FeSO system, ferric sulfur oxide system. So you can see all the species inside there. There are lots of name of chemical products on the chart here. On the left hand side is log S. Log S sub 2 means S2. This one log PO2 means oxygen partial pressure. So when you have this high temperature system, you can collect all the species depending on um, the oxygen concentration and also the sulfur S2 concentration, then you fall under each region here. For example, this region, again, this is a negative, log negative. This one also negative, 0, positive. So, all right. Then on this chart, you will see ferrum, this square. Then you have ferrum oxide this here also, and different properties here. So when you have different PO oxide, so not PO oxide, the oxygen concentration and your SO2 concentration, so S2 concentration, you can land at different regions of this one. Okay, this one is to show you that there have been research done on the formation of oxide. Okay. So this is the table. There are lots of graph here. So I just take one. So in the textbook, there are lots of, I think there are 3 or 4 example of graph, but basically most of them, they are same. But the concept is that you know what happened to your y-axis and x-axis and what is inside the diagram. What inside the stability diagram? You have all the oxide region that you can see. Next, we go into kinetic principle. So kinetic principle, there are few steps that we'll look at on how the formation of oxide. Right? First, you talk about absorption of oxygen on the metals. All right? There are few procedures on how oxide form. First, you absorb oxygen, and this process happen on the surface of metals. So first you focus on oxygen, you go and grab oxygen from the environment, then you start to form oxide already. So how oxide form? When the oxygen and the metals join together, still back to the general equation, M plus O2, you get MO2. So it will start with nucleation, means a very small oxide, and then it start to grow. Okay, start to grow. The oxide start to grow bigger and bigger until it reach a state where you can see oxide film on the surface. Okay, so when you talk about high temperature oxidation, you talk about oxygen and the metals. You give the equation of the metals, M plus O2, you get MO2. Then you start with explaining the physical bonding, physical creation. You start with the nuclear, and then you start to grow and become oxide. Okay, it's like a storytelling. Okay, so when you start to grow oxide and you start to increase the temperature, so on, you still remember before the break, they are they are 7, right? 7 or 9. There is one how the oxide can form, right? So you have low temperature, medium temperature, and high temperature. So when you reach high temperature, what happened to the oxide? So you start to have the crack on the oxide film. So then the crack will become defect. Defect means something that is not good to the structure. Defect, we have defect, or we call it a micro crack or macro crack. Micro crack means very small crack. Macro means the growth of micro crack become bigger. And then porosity means hole, the hole inside the material. Okay, hole inside material because of the metals element was taken away during the oxidation process. So this is one of the photo that you can find in the refinery when you have a metals element that transfer or connect the pipe that transfer in a very high temperature. So if you do not maintain it, so you will see all these high temperature corrosion happen on the surface. And if you leave it there, you will have a micro crack that you will make this connector to burst. Right. So if you work in the oil and gas industry later, just be careful when you are assigned to the inspection team or structure integrity inspection team. Just make sure you look into all this area. Okay. Next, we go into the Pauling backward relationship, PB relationship. So what does this PB relationship mean? So we talk what is involved in this equation. We talk about oxide. We talk about metals again, oxide and metals. And for PB relationship or PB equation, we use volume to calculate. So again, for high temperature corrosion, when it comes to oxidation, you only talk about two chemical components, oxygens and metals. And remember the equation M plus O2, you get MO2. Okay, so by using the volume of oxide and oxygen, you able to predict the degree of protection by the scale, because you know that the oxides, when it start to form a film on the metals, it is good. At the early stage, it is good for protection. But if you continue to increase temperature, this oxide going to become brittle and have a micro crack and macro crack and become crack that you can visually see, and it will destroy the integrity, the structure integrity of the structure. So I can see, I hope you can see the development of the corrosion itself. All right. So there are two conditions. So one is if the oxide volume is low, then something will destroy the oxide layer, which is tensile stress. You know tensile stress, but tensile means you're pulling at both ends. The stress that you're pulling at both ends. You have a few form of stress. You have tensile stress, compressive stress, and then you have torsion, you have bending. So when you have tensile stress with pulling at both ends, or when you have a metal body, that when you have a high temperature, what happened to the tube? You imagine the tube that transfer high energy liquid. So what happened to the metal tube? It will expand, right? So if you have a tube, so it will expand, right? So when it expand, what happened? If you look at element on the wall, it will pulling at both ends. So pulling at both ends means fall under tensile stress. So when your oxide volume is low, then the tensile stress will crack the oxide layer. However, if the oxide level is high, so if the oxide volume is high, so what happened in the layer, in the oxide layer? It will attack the the adversity or the connection between the oxide and the metal surface. All right. So under two conditions, when the oxide level volume is low, so what we're going to destroy it? What happens if the oxide level is volume is high? So what happened to the breakup of the metals and oxide? Okay. So there are two conditions here. Huh? Okay. So qualitatively, you can say when we talk about protection on the metals because of the oxide level, so the best condition that provide protection to the metals is at a condition where the volume of oxide is same with the metal consumed. Because you're talking about M plus O2, M plus O2, you get MO2, right? M plus O2, you get M plus O2 to MO2. So on the MO2 is the oxide form. So if the oxide form is the same as the metals that consume, then that is the degree of the optimum protection that you have. Okay. If the volume of oxide and the metal consumed do not balance, then the level of protection is not that good. Okay. All right. So this is just a very qualitatively explain about the protection. The protection can be done by balancing the oxide and the metals consumed. Okay, oxide and metal consumed. They are related with PB equation later on. Yeah. So this slide just show you what is the logic behind the equation later. All right. Okay, so this equation here. So I think this one is the first equation for this chapter. PB, or the peeling backward relationship. So again, PB tie to the protection of on the metals at high corrosion, high temperature corrosion perspective or chapter. So PB link with oxide and the metal consumed. So you take oxide, the volume of oxide that you can find, divided by the volume of the metal consumed, the metal consumer. So the best way, from the statement just now, the best way of protection you reach when the top volume equal to or similar, very near to metal consumed. Then you get the best protection. All right. So these are the equation, but this is the fundamental concept. The rest equation is just normal mathematics to find the volume. Right? You know the equation to find volume if you're given a certain parameter, right? All right. So this is one of it, lah. This is one of it. This is a textbook equation given. So how do you find the volume produced and the volume metal consumed? You use all these parameters. So molecule weight of the oxide, density of the oxide, number of metal atom in the oxide. Because why we use metal atoms, number of atoms? Because in our calculation for chemistry, we use mole. You still remember mole? How many mole in the solution, or how many mole in the chemicals reaction? So we need, from the mole itself, you can calculate the number of metal atom, density of the metals, and atomic weight of the metals. Okay, so this is the final equation you get after you rearrange the equation. So I put some equation for you to relate to all these parameter here. Before I show you the derivation steps, just bear in mind that PV numbers, after you've done calculation, if it's more than 1, if the ratio is more than 1 or around 1, that consider optimum condition, optimum protection condition. All right. So remember this simple equation. In test or exam, maybe I will test you on this, the value of the what is the meaning of PV value. What is the meaning of PV value? What do you understand about it? So maybe I'll give you some value to calculate the volume. Then you find out the ratio, and then you tell me, you compare two scenarios, scenario A, scenario B. I'll give you a table, scenario A, scenario B. You plug in the numbers to calculate the volume of oxide produced, the volume of metal consumed. You compare two scenarios, A and B, one to another. So if you have a PV ratio more than 1 or higher, that means that is the more favorable scenario that you go, or you call it the protection level is higher if you compare two scenarios. Yeah. So the rest is just a derivation of this equation, right? Because this one is already rearranged. So at the first look, you might not able to get why this is over there, right? Why there's a mixture of oxide and metal in this um, in this formula here. So you know that the volume of oxide you can calculate in a chemical form. So here we take a molar volume. Although here this is oversimplified already, but the volume we use here is in molar volume. On the top is oxide, so I put as V oxide. The bottom one is N. N is this one. N is the number of metal atom times the molar volume of the metals. So this form the basic calculation for PB, or peeling backward relationship. Then the rest is just to recall your chemistries. How do you find the density of something? Density, you take mass divided by volume, correct? How you calculate density? You take mass divided by volume. But in this case, you look at molecular level. So let's say I put an example to find the density of the oxide. How you find the density of the oxide? You take the oxide mass divided by volume of the oxide. And in this case, in the molecular mass divided by molar volume. Again, you still back to the basic density equal to mass divided by volume. And then you expand this one using the chemistry equation. Recall this one will be the same. So I rearrange this equation to get my volume of my oxide. How do I get my volume of oxide? I pull my equation, this one, to the left, and I pull my density to below. So I get this equation. Basically, these two are still definition of density. Okay, but I rearrange the equation, I get volume of oxide. So this is one of the example how you get the volume of oxide on the top. Okay, how you get the volume of oxide on the top? You're taking molecular mass divided by density. All right, so that's why how you get mass, how you get mass for oxide? You get molecule weight multiplied by density, not density, density of oxide. Density of oxide D here. That's why you see mass of oxide. Where's mass of? Okay, mass of oxide. W divided by D in here. And then the another component is N I copy. Then you do the same derivation for volume for metals. So volume of metals, you just switch. Volume metals also same. Mass divided by density. But in this case, because it's mass divided by density, so you know that you have divide relationship. You can pull your density to the top, right? So that's why you have a D over here. Okay, so this is just a detailed explanation on how this equation form. But as long as you understand what is PV relationship, is oxide divided by metals component. Okay, volume of oxide divided by volume metal consumed in the corrosion process. Any question for this equation? Good, everyone good?
Yes, okay, sir.
Yeah. Okay. So again, how do we come up with a question with this equation in the exam or test? We might give you a table with two set of scenario. Scenario A, scenario B, then we'll give you the metal consumed, oxide consumed. Maybe I'll give you some data here. I'll give you the molecule weight and so on. Then you calculate. All right. Then you compare two scenarios. Is this the scenario A is scenario B? They are in the good optimum protection level. Okay. So if you get the value more than 1, if you get the protection value more than 1, it means you are reaching the optimum protection for the corrosion. Okay, if you get less than 1, means there is a protection but not strong enough. Okay, there's still a loss of metals losses in the process. Okay, you can see the ratio, right? How you get less than 1 means your denominator is bigger than the top, right? So when you denominator this one, metal consumed is more than the oxide produced, means the corrosion is keep on happening. Okay, and the surface is being consumed by the corrosion. So this one tell you the ratio. How good is the protection, right? Yeah, these are further lah. Okay. Okay, another one is that sadly to say, in practical, PB has been found that they are generally poor prediction for actual protection of scale, because one region or one argument about the PV relationship here, in the context of high temperature corrosion, is a very complex chemical process. You cannot identify the oxide happen inside there, because you're involved in the high temperature and high flow environment. You cannot trace the percentage of oxide at that particular time for a long period of time. Means that the data will keep changing and it's very complex. It might happen, the metal might consume not because of corrosion, maybe because of other foreign body or other things, right? Because it's just measure the metal consumed and the oxide produced. So it might, other types of corrosion might contribute to all these values. So I just highlight this one. There is a way to calculate PV relationship, and it can tell you the level of protection. However, in practical, it's very hard to get the presentable value for evaluation. Okay, but there's a way, right? There's a way to calculate the protection level. So you can see here, there's a table here. So this one is the oxide metal volume ratio for some common metals. Okay, so oxide metal values. So these are all the oxide, and what happened to the ratio of the oxide over metals, meaning this one, the PV value. Okay, PV value here. This is called PV value, where you can, in short, you can say oxide over metals is a oxide over metals ratio, okay, per volume. So as you can see here, from this table, right? From this table, from the statement just now, if your PV, excuse me, if your PV value more than 1 means you are reaching optimum protection. So on this table, you can see that there are lots of good protection here. Okay, weak protection, good protection, best protection. Okay, higher and higher, but higher means something. The more, you still remember there are two scenarios. What happened to the low level of oxide, low volume of oxide, and what happened to the high level of oxide? Low level of oxide, you can destroy with the tensile stress, and if you have a high oxide volume, the aversive between the oxide and the metals, it can be creating stress there. Okay, so just take note on this one, on how to read all this value. Okay, so from this table, you know which one is a good protection and which one is better from each other from the value. As long as more than 1, you are in good hand. It means you are in a good protection level, but don't go for too high. For example, this one, right? 3, I think a bit too much lah. Okay, so what I mean by, for example, this one 3. What I mean by 3 means you can imagine this one 3, this one 1. In if oxide produced is 3 times more than your metals consumed, okay, then it will create some other problems on the oxide layer. Okay, yeah, this is just a recall what happened to the PV. Okay, we go for a few more slides. So we have done with PV relationship. By looking at the table, you know how to make a good judgment, which one can give you protection. Right? Protection from corrosion, protection from corrosion in the context of high temperature corrosion. Don't mix with other corrosion. PV works for high temperature corrosion. Don't mix with the other chapter that we learned before this. Don't mix with chapter 1, chapter 2, and chapter 3. Now we are at a high temperature corrosion. Okay, now we talk about rate. How fast the corrosion rate people measure or conduct research in this area. Okay, now we talk about how fast the corrosion can happen. There are 3 laws. There are 3 laws that use to calculate. But before that, we look at micro mechanism. Okay. Now, micro mechanism means that you look into the structure, microstructure of the oxide. All right. So meaning you study based under microscopic studies. You cut the oxide into half, then you look at the structure, and then you do some experiment on the oxide itself. And you learned about material before. So when you talk about material, there's one structure called lattice, ionic lattice. So there will be defect on these lattices. Lattices you can imagine as a cubic form, and there's a loss of wireframe. It's like a Lego. It's like a Lego bricks that tell you where is the location of that particular particles. So there are three categories under oxide microstructure. The rest you can read, but I highlight the main point under micromechanism or microstructure, oxide microstructure. There are three types. So one is positive type, one is negative type and negative type. Positive type, you have positive P type. P type means positive type. Means you create a positive charge. Okay, positive charge metals. You know that metals always give positive charge, right? Fe2 positive, M positive, aluminium 3 positive. So the first oxide microstructure is related to metals. So metals always carry positive charge. So P-type metal deficit oxide. Okay, so they fall into the metal cation vacancy. So the first one link with the metals. The rest you can read, right? Second type is the negative type. Negative type metal. Sometimes you get oxide in the negative charges. You will fill into the defect means there is a you imagine you have a leg you have a Rubik you have a Rubik cube, and one of the point is missing. We call defect. So all this will fill inside that hole. The third one is the negative type cation, anion. One is cation, one is anion. Vacancy oxide that have oxygen. One is oxide, one is oxygen. So you have three scenario for the oxide microstructure. You have under oxide microstructure, you have three category of defect. Okay, meaning if you take a high temperature corrosion sample, you cut that open, and then you observe them under microscope, and then you run some chemical analysis on the content of the oxide, right? Then you'll find three types of defect or three types of oxide from under this high temperature corrosion. Positive type metal deficit oxide, negative type caution interstitial metal oxide, meaning this second type is have more metals element in the oxide. Next one is the oxide that contain oxygen. So sometimes the oxide will capture oxygen. Sometimes the oxide will capture metals. So these are the two main difference between the oxide. And then this one is only metals component. Okay, so you have three types of oxide in microstructure. Okay, so I hope you guys can differentiate them. Next one, we look at oxidation reaction. Okay, we will use some concept that we learned in chapter 2 under aqueous corrosion for high temperature oxidation reaction. They are quite similar, only at high temperature corrosion, you don't have liquid. You don't have, means that you don't have water surround the metals. It's a dry corrosion. Okay, it's a dry corrosion under high temperature, but the process still, some of the chemical process we can still use. For example, the formation of metal oxide. So metal plus oxygen, you get MO. Then within this process, you have another two process actually happen. So when you write reaction for the oxidation process is metals plus, you can write this one as, this one is formation of metal monoxide. Metal monoxide means one oxygen only. So you only need half of the oxygen. But you know that when you want to break oxygen into atom, you need to break the electron, electrovalence connection. So what you do is that your metals will break into positive charge and negative charge. Okay, this is how the corrosion starts already. Your metal will break into positive charge and negative charge, and this negative charge will supply to the oxygen. So when oxygen receives negative charge, it will become negative charge. In this case, we only focus on oxygen atom, O, become O negative. Okay, so I think this one is direct chemical reaction. And be sensitive to these two words. Anodic reaction. Anodic reaction is always linked with the metals they break into negative charge. Okay, not negative charge. The metals will break into positive and negative charge, but they contribute negative charge. These fall under anodic reaction. Another one, if the element receives charge, then you will get catalytic reaction. These are the two popular process that we like to ask in test or final exam. Okay, even in your test one also, right? Even your test one, you start seeing that we start asking, what is the anodic reaction? What is the catalytic reaction? So take note on these two. On the oxidation process, we are now at the oxidation process. What is happen in oxidation process? Write the anodic reaction and catalytic reaction. Okay, so these are the answer that we expect in your answer sheet. Any question? Any question so far?
No, sir.
Good, eh?
No, sir.
All right, good, excellent. Next, we look at a few chart. Then we call it a day. Okay, a few chart. This is, you still remember we have three types of oxide when we cut open. We have P type. Okay, just now, go back to the one slide here. Remember we have three types of oxide. There are three types of oxide in the microstructure element. So we have three types of oxide when you cut open the sample. First, you will have positive oxide, or you can say as a metal oxide, only contain metals. Another one is negative one. So the second one is the oxide contain metals, but not as many as the first one. Another one is his contain oxygen. He will capture oxygen for the oxide. There are three types of microstructure there. So we look at, I will show you the chart for this in each one of these oxide. So the first one is the negative type cation interstitial oxide. This one in the gas scenario. So this one is the N-type, N-type cation interstitial oxide at oxide gas interface. So on this diagram, you have three layer. You have three layer, gas and metals. Metal substrate means the corroding body. You have metals, gas, and of course, when we talk about oxidation, you have an oxide layer in the middle. Okay, so watch carefully what happened to the chemical process. Your metals will always break into electric charge. So in here, we have our metal contribute two electric charge negative. What happened to our oxide here and our gas here? So our gas will receive electron and become O negative charge. And sometimes this one is for oxygen. And through the oxide itself, the metal's positive charge will combine with the oxygen charge. It will drop back. It will form MO, means the oxide. So this oxide, because it's a precipitation, is a solid powder. You can see as a powder or atom that have weight. So this one will drop back to the surface of the oxide. Then it start to build layer by layer, become an oxide layer. So I hope you see the process in this schematic diagram here. Okay, so this one under negative type caution interstitial oxide. So meaning metals break into electron, then it combine with the gas. So where is the electron go? Electron will combine with the oxygen. The oxygen get electron charge, become negative, and the metal element, when they break into charges, so they will float into the air and combine with the negative charge of oxygen, become metal oxide, monoxide here, MO. So this one is the oxide element. Oxide element have weight, so it will fall back to the surface, and it continue the process until stabilize, or until the metal is consumed, or the gas is no longer able to sustain the chemical process, or we call it equilibrium process. Right, so this is the first step. I think this one is more easier to understand. Next, we move on to the next one. I show you another one. So this one is N-type, anion vacancy oxide, and this one, the films will appear in the oxide interface. What I mean by oxide interface with this here? So oxide interface sometimes on the top, sometimes on the left, or on the bottom. All right. So same process as you can see here, but something happened, something different from the neighbor over here. So the general process still same. Metal contribute, metal become two charges, metal two positive and two negative. So then you ask yourself question, what happened to M positive? What happened to two electron negative? They will combine with the gas. So what is oxidation happen? In high temperature corrosion, we talk about oxidation. Oxidation means you combine with oxygen, right? So which one combine with oxygen? So you start with the electron first. Electron will combine with the oxygen. Oxygen will become negative charge. Then after that, the M2 positive, right? So M2 positive here, it will still go up, but they will combine and it fall back. Okay, it combine and then it fall back. So here you see the M combined with positive charge. The charges happen at interface of oxide and metal substrate. Here, the previous one, the product is above, you can say as above the oxide and the gas layer here. The metal charges will go to the surface of the oxide and they will deposit here. But for the second type, they'll go and combine and then they fall back and form a layer between the interface here. So I hope you can see the differences. Although the process is similar, or can say same, but the location of all this oxide is a bit different. One is on the top layer here, one as here, because it's fall back to, because of the oxygen go inside the oxide and combine with the metal over here. Okay, this one combined with the top over here. Okay, I hope you can see the differences, yeah? Okay, then the next one. Okay, these two are negative type, so it's more easy to compare side by side. The next one, I show you the positive one, the positive type. So the positive type, right? So you see the equation over here. Again, you have 3 layer, gas, oxide, and metal. Again, in exam, this question come out to ask you to explain oxidation reaction using schematic diagram, meaning we expect you to draw 3 layer diagram, gas, oxide, and metal, and then you explain with all these equation. Okay, look at positive one. Positive one, what happened to metal? Still the same. Your metal still change to charges, 2 positive, 2 negative. You see what happened to the charges? The charges will go up. Okay, the gases also will break. So the gases will receive electron, become O2 negative, same like the previous one. And the metal also form on the surface here. Okay, the metal will go up, combine with the oxygen charges, become metal oxide. Or in this case, MO. MO is a monoxide, but it's still under oxide category. So after it combine, it will form, then you will see that the cation vacancy will go down. Cation vacancy means the positive charge location, it will go down here. And then this one, you see the electron hole will go down. This one is more on, it's very hard to observe under microscope. This one happened in very fast rate, and also again high temperature. So to get a very high quality microscope that can observe molecule movement at a high temperature, high resolution, I don't think a lot of institution afford to buy such an equipment or develop such an equipment. Yeah. So, but what is the differences between the previous two? For the P-type is the movement of the vacancies for electron and cation. So both move down from the surface. Okay. The rest you can read from here. Okay. Yeah. So for positive charge here, for P-type here, you can see there's one more process on the surface here. So one interesting phenomena for positive type metal deficit oxide, right? So the metal positive charge, 2 positive here, when it move up, right? When it move up, it will, don't know somehow, the metals itself, he tried to push one more electron from the electron valence itself. Meaning when the metals reach the surface, somehow the metals kick out 1 electron from itself, means it contribute 1 more electron to itself. It become 3 positive charge, right? And then it contribute to the gases here and so on. And then 3 positive here, it will come down and it will combine with the electron at the metal surface here. Then it will form 2 positive again. Then it will go up again, and then repeat 1 more process over here. So you can see for P-type metal deficit oxide, it involves the movement of 2 positive. That is, and then because of the movement of 2 positive, and because of the behavior of 2 positive, I don't know, somehow this one become naughty, and it contribute 1 electron, means it kick out 1 electron from itself. It become more positive charge, right? 2 positive, you kick out 1 electron, it become 3 positive. So 3 positive will move down. It will move down. Why it will move down? Remember, why it move down? Because positive and negative charge, they will attract to each other, right? Because this metal subtract, they contribute, they are producing electron negative here. Means this one become negative region. So the positive charge, if you compare 2 positive and 3 positive, which one will swim down first? Is a 3 positive, right? So 3 positive will swim down to attach to this area and receive electron, and then two negative will swim up again. So the process will happen here. Okay, so just as a summary for p-type is that you focus on what happened to M2 positive activity inside oxide. Okay, then it gives you the cation vacancy and electron holes. Move down from the surface. Okay. Hope you guys can get the idea. Okay, I think we stop here because of the time. All right, let me stop the recording. Any questions so far? No, right? Any question?
No, sir.
Right. You guys have class